Hello, thank you for watching. In this lesson, you will learn how to identify the domain and range of a function and also determine if a relation can be classified as a function. We'll begin by first reviewing what a relation is. A relation is just simply any set of ordered pairs. So if you're talking about, again, this set here, right here in the middle, all right, that is a relation. Now, a relation can be represented as a mapping, as a set of ordered pairs, whether organized like this, or in a T charts, we have labeled X and Y, or in a graph. These all represent relations. And we're going to begin today is by going over how to identify the domain on a relation. The domain of a relation is going to simply be the X coordinates in that relation. So here in this relation, these three numbers will be considered to be the domain. And as you can see, again, the various representations, the domain is the same three numbers, 2, 3, and 4. The range of a relation is simply the y coordinates of that relation. So in this situation, it would be -2, -1, 0, 0, -1, and -2. Again, it's all the y values. Now with discrete data, it's really easy to identify the domain and the range because it's simply going to be, again, a set of a point. Like in this example right here, our domain is the x values of our relation. So -1, 7, 3, and -5. And the range are the y coordinates of our relation. So -1, 4, and 0. Now normally you would like to put these in order, but again, if you don't, that's fine. If you have a table of values again, a graph, like you see right here, this discrete set of data points, again, our relation is just simply going to be our x values. So this point here, this point down here, which is located at -3, -4, -1, 5. This location is 1, 2. This is at 2, 0. And this is 1, -3. So simply figuring out again the location, the coordinates of these 5 points that create this relation, we can identify again the domain as -3, -1, +1, and 2. Notice that 1 is being used twice, so I'm not going to write it in my set here. I'm only going to write it once. No reason to write the number twice since it's being repeated. And my range is -4, -3, 0, 2, and 5. And this one, well, this is a lot easier because again, it's already labeling the x values and the y values in a mapping. So this is my domain. Again, these 5 numbers highlighted here in yellow, and the range are all the y values highlighted in blue. Now, the more challenging part is identifying the domain and range when we have a continuous graph, like this one right here. Well, again, when we're trying to do determining, again, on any situation, for any relation in determining the domain and range, we want to basically list all of the x coordinates and all the y coordinates. So in this situation here, it's a little bit more tougher because, well, obviously we can't list everything because it's continuous. Remember, again, there's an infinite number of values between any two integers. So here I can't say that my domain is going to simply be all the numbers between, or are going to be the numbers between +1 and 1, 2, 3, 4, and -4, or -4 to +1. Because first of all, -4 doesn't count because of the open circle right there. And then again, -3, -2, -1, 0, and 1 are not the only numbers again that make up this graph for x. This graph has x coordinates or has coordinates where the x value is going to be between, and then it's going to have x coordinates between those. So it's an infinite number of x coordinates between here and here. So between here and here. So the way we're going to represent our domain here is by using interval notation. And since the graph exists only from -4 to -1, we're going to list this using interval notation. It kind of looks like an ordered pair, but in interval notation, we're going to use a closed bracket on the closed circle and an open bracket or parentheses on the open circle. So this is a half interval here. And for the range, well, again, the graph exists above this red horizontal line and below this red horizontal line. So that means that all of the y values are going to be between -7 and +2. And in this situation, since both ends are closed, this is a closed interval. And the reason, again, before I move on to the next example, the reason that we're using, again, interval notation and not listing the numbers -6, -2, all the way to +2 is because this is only counting the integers. We're not considering, again, anything in between those integers. So in order to consider all of the values from -7 to +2, we use interval notation. So that's the difference between a discrete data set, like on this example, where I can just simply list all of the x values and list all of the y values because it's only made out of these 5 points there. And this example here, where I have to write an interval notation to include all of the numbers between -7 and +2, and all the numbers greater than -4 up to +1. Now, if one end doesn't have a endpoint and one does, and the other end does, again, we just still do the exact same thing. We'll start again with the horizontal. Well, this graph exists to the right. Do it in blue. It exists to the right of this endpoint right here, which is at -3. And notice that the other end doesn't stop. It continues moving. So that means, again, that this graph right here is going to have x coordinates. All of the coordinates that make this are going to be values of x, the domain, that's going to be greater than -3. So here our domain is going to go from -3 to +infinity. And for infinity, it's an open interval on that end right here. It's a half interval where one end is closed, the other end is open, because again, infinity is not an actual number, it's just an idea. So obviously we can't include that number, thus it's open. And for the range, do this in red, the graph only exists above this red line here, which is at -4, well, the y value of -4. So that means that our range is all of the y values greater than -4, which is written like this in interval notation. So this means that y will be greater than or equal to -4, while the one on top says that x, all of the x coordinates for this function or for this relation, because we haven't talked about functions yet, is greater than -3. Now for an example like this, there's two ways to think about this. We consider this again as a piecewise function where we have a piece to the left and we have another piece to the right. So since this horizontal line this vertical line right here exists at x is equal to -2, then there's two possibilities. To the left, the domain would be all the values from negative infinity to negative 2. Of course, we would stop at negative 2 because of the open circle right there. And the domain is also then unioned with all of the intervals to the right. So from negative 2 to infinity. So what this is stating is basically, again, that the domain is all of the values from negative 2, well, let me do it like this, from negative 2 to infinity. I'm sorry, from negative infinity to positive negative 2, and then from negative 2 all the way to positive infinity. So these two sections of this graph here are going to have x values that can fall anywhere between those numbers there. And the same thing with the range. Similar idea. Since our range can be found in the following location, similar situation. Here, this is at negative 3. This simply just changes the value to negative 3. Because the y value, that horizontal line, is negative 3. Because again, the location of this point here is located at negative 2, negative 3. So the domain is going to be all real numbers except for this x value of negative 2. So we say we stop at negative 2. We basically jump over that and continue from negative 2 all the way to infinity. And notice again, it's open intervals because we're not including negative 2. And the same thing again vertically, finding the values of the range, all the y coordinates of this line. So it will be all the values from negative infinity to positive infinity with the exception of negative 3, which again leads us to a different way of thinking about this. Another way of thinking about this is to simply say that the domain will be everything except for negative 2. So we can write this interval here can be written in that format, which means this interval here can be written as simply stating that y cannot equal to negative 3 because again of that open circle there. Now for this example right here, the domain for this is going to be all real numbers. Notice again that the graph again continues to the left and to the right. So it's not going to stop, so thus the domain would be all x values. There's no boundary point on the left, no boundary on the right. So it's going to be all x values from negative infinity to positive infinity. Now we have to assume again that the graph is going to follow the same pattern and is going to again make the parabolic again shape. So that means that the highest point that the graph reaches is this horizontal line at 5, and the lowest that it reaches is the horizontal line y is equal to negative 5. So the range of this function would be all of the y values between negative 5 and positive 5. Now anytime we're looking for the domain and range, what we're basically just essentially looking for is all of the possible y values and all of the possible x values for this function. Like if I pick any point on the graph, like that one right there, I know that the x value is going to be any number from negative infinity to positive infinity. And I know the y value is going to have to be a number between negative 5 and positive 5. That's what we're focusing on, what the purpose of identifying the domain and range is. Being able to have a reasonable solution and inputs first, a reasonable input, what numbers can I plug in, and what number should I get out when I plug that number into my function. So whatever this function is, and again I'm getting ahead of myself with the word function, but whatever the equation to this relation is that creates this shape here, I know that I can plug in any value of x from negative infinity to positive infinity. And when I do that, my answer has to be a number between negative 5 and positive 5, just by looking at the graph. So again, that gives me a reasonableness that if I plug something in and plug a number in, since I have no problem plugging anything in, and my answer doesn't come out to be between -5 and +5, that I must have done something wrong with my calculations. And this is the purpose again of domain and range, and what the domain and range is supposed to help us out with. Now, let's discuss again a function. Now, some relations can be identified as functions because of this characteristic that they have. That for every domain, meaning that every x coordinates, there is only one value in the range. So in terms of a mapping, or again, ordered pair, that means that these values that I plug in can only give me one answer out of it. So if I had an equation, y is equal to x squared plus 4, whatever number I plug in for x, following again my rules here over the order operations, there's only one possible answer that's going to come out. If that's true, then that's going to be classified as a function. In very layman's terms, what this simply means is that if an x value is used more than once or mapped to a second number, then that relation cannot be classified as a function. So for example, here among these three different relations, -3, -1, 2, and 5 are only mapped or paired with only one value of y. -3 is only mapped with -4, the same with -1 to -2, 2 to 1, 5 to 1. So this right here would be a function. Same thing with the second one. This is a function. And I know people get this one confused because they see the number 2, but -7 is only mapped to the number 2, and -5 is only mapped to the number 2. If -5 was mapped to the number 8 as well, or something else, then it wouldn't be a function. But because -7 has only paired up with one y value, it's a function. It doesn't matter that another number is also paired up to the same y value. That doesn't matter. Just as long as this doesn't get paired up to its second number. And the same thing with any one of these values here. As long as any one of these four numbers does not get paired up to a second value, then it's going to be a function. Unlike number 10, this is exactly what I'm referring to. In example 10, -9 is paired up to two values in the range. So this is not a function. It's a relation, still a relation. All of these examples are all examples of relations, but this relation is, these two relations are functions, while this last relation is not a function. Now, if we have a graph, the way we determine if a graph is a function is by using the vertical line test. So if a vertical line intersects only one part of our data of our relation, or our continuous relation or discrete relation, as you see in these examples right here, then it's going to be a function. However, if our vertical line touches our relation more than once, as you see here, it touches everywhere, and over here it touches up there, or this vertical line that touches up there and down there, then these are not going to be functions. For example, this here is a function because the vertical line will touch only in one location. Each one of these vertical lines touches the relation in one location. It touches down here. This yellow vertical line touches there, and this vertical line touches there. So this would be classified as a function. And number 12, this is not a function, because our vertical line, sorry, I meant to draw a vertical line here. Let me fix this. Because if I draw a vertical line right here, let's say, we can clearly see again that we touch the graph in two different locations. So that means that x is equal to 2. If I represent this as a mapping, we have 2 points. We have this point up here, which looks to be like 2.5, and we have this point down there which looks to be around negative 0.4. So it's being mapped to two different locations. So this is not a function. Now we can use this idea again to identify equations and whether equations are functions or not. Like in this example right here, if I was to graph this, rewrite this and graph this, I would see that this is a function, because I would see that this creates a parabola like this, and according to the vertical line test, this will pass. So this is going to be a function. Now let's say I couldn't graph this, and again, and I don't want to graph this and I want to save myself some time. Well, there's a shortcut and a very easy rule to identify whether an equation is a function or not. Simply by looking at the the exponent on y. If the exponent of y is an odd number, like this example right here where this number is 1, then that equation is going to be a function. However, if the exponent on our y term is an even power, like the one right here, 6, then this equation will graph something that is not a function. Because what we end up doing when we solve this equation, we end up having a positive and negative root, which in this case will be the root 6. And we end up creating a graph, something similar to this, where it's going to look like some type of C or a circle. It's going to do something again where it behaves such in a form where the top part and the bottom part are going to overlap on our relation here, on our equation. So we end up creating something like this. And this happens every single time y is raised to an even power. Now here, because of the x to the third, it looks a lot different than what I'm graphing right here, but just this is the easiest example I can give you, okay? Like a easiest representation I can give you, but something like this is gonna happen. It could be again that it curves, all right, it looks something, a little curvature, but the idea is that eventually you're gonna have two ends again that touch when you draw a vertical line through it. So the vertical line test, it fails the vertical line test and thus is not a function. So for example, the next one right here, since on this example y is raised to the 5th power, an odd exponent, this is going to be a function, because we're not going to get a situation where y is going to equal to both a positive and negative radical. Okay, here we just would end up with either just a positive or just a negative, but not both of them. And in the last example, because y is raised to the 2nd power, this one would give us a positive and negative radical value. So this would not be a function. Okay, so this concludes the lesson on relations and functions. If you have any questions, again, don't hesitate to email me. Again, thank you for watching, and I hope you have a great day.